potential energy of a system of 2-point charges. Now the concept of potential energy arises if we have to displace an object from one position to another against some external force. For example, we consider, say, two mass object M1 and M2. So we have two mass object M1 and M2, and suppose the two mass object is connected by a spring. Now if we displace these two mass object from their position, from their respective position, initial position, to this position. Suppose we're displacing it from the respective position to this position against the restoring force of the spring. And this spring will be compressed, and there will be a potential energy stored in this spring. So if we displace it from this position, initial position, to the final position, there will be a potential energy stored in the spring. So that if you release the two mass object, then what will happen is this mass M1 will move in this direction and M2 will move in this direction. So if we compress it, there's a potential energy. If we release it, these two objects again will go back to their initial position. Similarly, if we stretch the string instead of compressing the spring, suppose we displace these two M1 and M2. So M1 and M2, you displace it in this direction. So M1 in this direction, M2 in this direction. Then what will happen is that the spring will be stretched. And again, there's a potential energy stored in the spring. So that if you release these 2-point object, what will happen is that these 2-point object, M1, M2, they will come towards one another. Okay, they will move towards one another. If we compress it, remember, they will move away from one another. If we stretch it, if we displace it from this position against the restoring force, okay, they will, after releasing the two mass object, they will come towards one another. So that is the concept of potential energy. Remember, if we displace two mass object against the restoring force, in this case, then there will be a potential energy stored in the spring. So similarly with charge particles. Suppose if we have 2-point charge particles, two positive point charge particles. One is Q1 and say another one is Q2. So one is Q1 and the other one is Q2. Now since they are both positive, there is a force of repulsion between them. So the force on Q2 is in this direction and the force on Q1 will be in this direction. So there is a force of repulsion between these two charges. Now if I bring the two charges close to one another, then what will happen is that I'll have to do work against the repulsive force. So we have here Q1, I bring it close to one another, then I'll have to do work against the repulsive force. So if I have to move the two charges in this direction, work has to be done against these repulsive force. Okay, so I'm displacing the two charged particles against some forces, in this case which is the repulsive force. Then since I'm displacing it against some forces, there will be a potential energy between these two charged particles, or there's a potential energy in this system of 2-point charges. So that if I release it, again these two will be repelled from one another. So that is the concept of potential energy of 2-point charges. Similarly, if we have 2-point charges, one is say negative and the other one is positive, then there's a force of attraction between them. So they are attracted to one another. Now if I displace this against the electrostatic force, the attractive force, I bring this here and this one in this position. So I'll have to do work against this attractive force. So they are attracted to one another, I'm bringing them away from one another. So again here also, since I'm doing work against the attractive force, there will be a potential energy stored in these two charges, Q1 and Q2. So we have potential energy stored in the system of 2-point charges. One is of a positive, and the other one is negative and positive. So only if we have to do work against the electrostatic force, then only the concept of potential energy arises. So that if I release them, they will come back to their same initial position. Even here also, if I release it, they will go back to their initial position. Now we shall find out the expression for the potential energy of a system of 2-point charges. So if we have 2-point charges, say Q1 and Q2, separated by some distance r, then the potential energy of this two charge system is defined as the work done in bringing these two charges from infinity to these position A and B against the electrostatic force. So in order to calculate the work done in bringing these two charges from infinity, we first consider that the charges are at infinity. So both the charges are at infinity. So we have point A and point B. So both these charges are at infinity. Now if we bring charge Q1 from infinity, see this Q1 is at infinity. So if we bring this one from infinity to this point A, we have charge Q1 at infinity, we bring it to this point A, then there is no other charges which opposes the charge Q1. So if there's no electrostatic force which opposes this charge Q1, the work done will be 0. So here if we bring charge Q1 from infinity to point A, the work done is 0. So we'll write that work done as the blue one, and this is 0. Then we have another charge Q2, and if we bring this charge Q2 from infinity to this point B, then there is an electrostatic force between the two charges. There's electrostatic force between Q1 and Q2. So work has to be done against that electrostatic force, and since work is there in overcoming the force, which is the electrostatic force, your W2, the work done in bringing this charge from infinity to this point B, it has some value, and that value can be found out by the definition of electrostatic potential. Okay, so first we consider this charge at A. Now this charge at A will produce an electric field around a space, and the potential, the electrostatic potential, say at this point B, which is at a distance r from the charge A, is given as V1 Q1 by 4 pi epsilon naught Q1 by R. So this is the potential, electrostatic potential at this point B due to charge Q1. That we have known. We have derived this formula, electric potential due to a point charge. Now again come to the definition of your potential, electrostatic potential. Okay, your electrostatic potential, V is defined as the work done in bringing a positive test charge from infinity to a point B per unit test charge. So this is the definition of your potential. This is from the concept of electrostatic potential. Now in this case, we are not bringing a test charge, but we are bringing a charge Q2. So the work done in bringing this charge Q2 from infinity to this point B will be given as this one, W, infinity to B, then divided by Q2. And the potential at this point B, we know it is equal to V1. Hence, this work in bringing the charge Q2 from infinity to point B against the electrostatic force will be equal to, so in this formula, I'll write this as W2. So this work done will be V1 Q2. Okay, so this work done I've written as W2, the work done in bringing the charge Q2 from infinity to that point B. So your W2 is equal to V1 Q2. Hence this W2, if you put the value of V1, will be equal to 1 by 4 pi epsilon naught. Then we have Q1 by R. Then we have Q2. So this is the work done in bringing the charge Q2 from infinity to this point B. So the total work done will now be equal to, so your W will now be equal to W1 plus W2. And W1 is the work done bringing charge Q1 from infinity to point A. W2 is the work done bringing charge Q2 from infinity to point B. And this is equal to 0, and this is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. So here what we have is your work done. It bringing the system of 2-point charges from infinity to their respective position A and B is 1 by 4 pi epsilon naught Q1 Q2 divided by R. And this work done is stored in this system of 2-point charges as a potential energy. So this work done can be written as U, and this U is the potential energy of a system of 2-point charges Q1 and Q2. Now the potential energy of the 2-point charges of system of 2-point charges can be negative or positive. If Q1 is negative and Q2 is positive, so for unlike charges, what we have is Q1, Q2, this is less than 0. Then for this charge, for these two charges, negative and positive, the potential energy, this will be negative. So if we have a negative potential energy, then the force between them is attractive. Then for like charges, what we have is, say, positive and positive, or negative and negative. Then the product Q1, Q2, this will be greater than 0, and in this case the potential energy will be positive. So if your potential energy is positive, the force between two charges, they are repulsive in nature, and if your potential energy is negative, then the electrostatic force between the two charges are attractive in nature. Now we come to potential energy of an electric dipole placed inside a uniform electric field. Now again, the concept of potential energy arises if we have to do some work against some force. So here we have an electric dipole. We consider an electric dipole placed inside a uniform electric field. So we have a uniform electric field which is represented by these parallel field line, and your electric dipole is placed in this position. We have a positive and negative charge separated by some finite distance. So this is an electric dipole, and the dipole moment is in this direction. So your P, or dipole moment, P is in this direction, and it makes an angle theta with the direction of the electric field E. So your P is in this direction, and makes an angle theta with the direction of the electric field E. Now we know that an electric dipole placed inside this uniform electric field will experience a torque. So if your dipole is in this position, then this dipole will experience a torque, and that torque will try to twist this dipole in this position. And your torque is equal to, the magnitude of the torque is equal to PE sine theta. This we have derived in chapter 1. So your torque, which will twist this dipole from this position to this position, making it align with the electric field, is given by this PE sine theta. So if we want the dipole to be in this position, alright, then we'll have to do some work. Okay, now the torque will twist the dipole in this position. We will have to do work against that torque to make the dipole in this position. So again, here work has to be done against the torque which is trying to twist the dipole in this position. So work is done against the torque, and since work is done against some forces, in this case is the torque, potential energy is stored in the dipole. Okay, so we'll derive the formula for the potential energy of the dipole placed inside an electric field. Okay, so suppose the dipole is at this position. I'll represent the electric field by only one line. Suppose the dipole is at this position. So we have positive and negative charge here. Now if we displace this dipole from this position to this position, so from this position we displace it to this position by a small amount of angle d theta, then the work has to be done against the torque experienced by the dipole. The torque will make the dipole be in this position, but we will have to do work to make this dipole from this position, to displace the dipole from this position to this position, and that torque is equal to PE sine theta. Okay, and the displacement in this case will be this d theta. So we have a displacement which is d theta and torque which is equal to PE sine theta. So the work done, the small work done in displacing the dipole from this position against the torque is given by dW, and this work done is equal to tau d theta. So this is a small amount of work done, and here your tau is equal to PE sine theta. So here PE sine theta d theta. This is a small amount of work done. Now if you want to find the work done, say in displacing a dipole from a position, say from this position, suppose we have a dipole initially at this position. So let this angle be theta 1, and you displace the dipole to this position. And let this angle here, this one will be theta 2. So if we displace the dipole from theta 1 from this position to this position, then the work done in displacing the dipole from this position to this position can be found out by integrating this small work done from the limit theta 1 to theta 2. This will be equal to integration in the limit theta 1 to theta 2 of this PE sine theta d theta. So now PE is constant, so we take it outside of the integration. Then you have integration of sine theta d theta, and this integration is equal to minus cos theta. So mathematically, from mathematical formula, integration of sine is equal to minus cos. So we write here, instead of this integration, we write minus cos theta with the limits theta 1 theta 2. And now we put the limits of theta 1 and theta 2. So what we'll get is PE, and upon putting the limit, we have upper limit minus cos theta 2, then then we have the lower limit, which is theta 1. So cos theta 1. Then minus, and this minus will be plus. So this will be plus. Hence, I can write this as cos theta 1 minus cos theta 2. So PE into cos theta 1 minus cos theta 2. So this is the work done in displacing the dipole from theta 1 to theta 2. And this work done will be stored in the dipole as a potential energy of the dipole. So U will be equal to, U is the potential energy and is equal to PE cos theta 1 minus theta 2. Theta 1 is the initial position or the initial angle, and theta 2 is the final position of the dipole. So now we shall take the initial position of the dipole to be at this position. Okay, so we have the electric field E. The initial position of the dipole is taken to be at this position, which is making an angle 90 degree with the electric field E. So your P vector is making an angle 90 degree with your electric field vector E. This is the initial position of the dipole. We take this to be the initial position because at this position the potential energy of the dipole is 0. Okay, so at this position the potential energy is 0. That's why we take it to be the initial position. And from this position, suppose we want to displace the dipole, say at this position, from this position to this position. So we're displacing this dipole in this position. And see, this angle here is theta. So the initial position, the angle is 90. The final position, the angle is theta. So here your theta 1 will be equal to 90 degree, which is the initial position, and theta 2 will be equal to theta. So put the value here. What you'll get is U to be equal to P cos of 90 minus cos of theta. And cos of 90 is equal to 0. So what we have, U, the potential energy, is equal to minus P cos theta. So if a dipole is at this position, it has a potential energy of minus P cos theta. So if a dipole is at this position, then your potential energy is minus Pe cos theta. Now we come to the special cases. Suppose your dipole is placed in this position. So this is your dipole. It's placed in this position, making an angle 90 degree with the direction of the electric field. So what will be the potential energy in this case? In this case, the potential energy will be minus Pe and cos of, since the angle here theta is 90, so we have cos of 90 degree. And this cos of 90 degree, this will be equal to 0. So your potential energy will be 0. So at this position, I have told you earlier that potential energy is equal to 0. So this is the first case. Then the second case would be when the dipole is in the direction of the electric field, or the dipole moment. So this is your positive and this is the negative. So here the dipole is aligned in the direction of the electric field. In this case the angle is 0. Okay, the dipole moment is in this direction, so your P is in this direction, same direction as that of the electric field. So your angle will be equal to 0. Hence the potential energy will be equal to minus Pe cos of 0 degree, and in this case the potential energy cos of 0 will be 1, so we have minus PE. So the potential energy for this case, when the dipole is in the direction of the electric field, is minus PE. And in this case, the dipole has a minimum potential energy. So the potential energy of the dipole is minimum. Then we come to the third case. When your dipole makes an angle 180 degree with the direction of the electric field. So we have positive charge here and the negative charge here. So in this case your P vector will be in this direction. So it makes an angle of 180 degree with this E. E is in this direction, so this angle here is 180 degree. So the potential energy in this case will be equal to minus PE cos of 180 degree, and cos of 180 degree is minus 1. So here the potential energy will be PE, and in this case it is a maximum potential energy. So dipole has a maximum potential energy when it is in this position. If it's in this position, it has a minimum potential energy, and if it is perpendicular to the electric field, it has a potential energy of 0.